Well, welcome to this session on Inband network telemetry, which will be presented by J.K. Lee, Senior Principal Engineer from Intel, and Mukesh Hira, Principal Engineer at VMware. Mukesh is one of my old colleagues from my old VMware days, and both of these guys have been working on in-band network telemetry for a long time, which is really one of the canonical use cases for P4. Certainly, it's one of the first things that I heard about many years back when P4 was really in its incubation as to why we could take advantage of having more programmability inside the network itself. So it's a really great study of how P4 is being put into practical applications. And we've got two people here ready to give you the history and tell you where it's going. So with that, I'll hand it over to Mukesh to get us started.
Thank you, Bruce. Thank you for the introduction, and welcome everybody to this talk on in-band network telemetry, the history, impact, and future directions. I will start off with a brief overview of what INT is and provide a historical perspective, and also talk about some of the key principles that we adopted when developing INT. And then JK will go deeper into the different modes that INT can operate in, the impact it has had on the industry and continues to have on the industry, and some of the future directions in terms of using INT for more closed loop control use cases. And then we'll end with a summary. So what is INT, and why did we do INT in the industry? So as we all know, lack of fine-grained visibility into networks has been a significant pain point. When we are debugging or root-causing problems in the context of compute or storage, we have a plethora of information. We have access to logs, support bundles. We know the state of the system precisely at the time when the problem happened. Even if the problem happened 12 hours ago, we are able to look at logs from that time and identify the problem. That has historically not been the case with networks. The troubleshooting tools that we've had for networks have been fairly primitive, limited to ping, trace route, some flow exports, traffic mirroring, packet capture. These are really not useful unless you're debugging the problem live. And even if you're debugging the problem live, they provide very limited information. So this makes root-causing transient problems especially challenging. For example, if your application team calls and says, we had an outage or we had poor performance at 3 a.m. last night, it's extremely challenging to say what was going on in the network and what was causing the problem. So INT changes the game by providing fine-grained visibility on a per packet basis and lets you answer questions like, on a per packet basis, what path did the packet take in the network? What state did it experience at each hop? Per hop latency, what is the queue occupancy, egress queue occupancy, what congestion did it experience at each hop? What other flows and that were simultaneously active, passing through the switch, causing that congestion, and so on. So let me explain with a picture the initial concept of INT. So the idea initially in the initial mode in which INT was developed was that a switch or an entity at the start of the INT domain, as you may call it, we call it the INT source, identifies that a particular flow is to be traced and state information for the flow in the network has to be captured, and it inserts instructions in the packet. That instructions specify what each transit INT hop in the network should do with the packet in terms of what state it needs to insert into the packet header, into the INT header. The state could be latency at that hop or egress queue occupancy or the whole bunch of metrics that the INT spec covers. So as the packet traverses these INT switches that implement INT, and it reaches the other end of the domain, we call it the INT sink. The INT sink can decapsulate the stack of metadata that every switch in the network has inserted, and then pass it on to an analytic engine or an INT monitor for each and every packet of the flow or a set of flows. And once that INT header is decapsulated, it then forwards the packet on. When the packet reaches the end host or the end application, the application just doesn't even know that INT happened underneath, or such debugging or troubleshooting or state gathering happened. And the analytic engine has a plethora of information in terms of what happened at each hop. So you can run through a bunch of analytics and troubleshoot and do a lot of good things with the information and the visibility you have in the network. So this was the initial mode of operation. JK will go into more details and to other modes that INT operates in now, or it does support now in addition to this. So brief historical perspective, the roots of INT are in some early work in papers published in SIGCOMM 2014, and there was a demo in SIGCOMM 2015. And then following that in 2015, there was an initial INT specification in the industry with a very limited set of participants. In 2017, the P4 applications working group was formed within p4.org with an initial focus on INT as the main use case. And that's when we got broader participation from companies including Cisco, Arista, VMware, Intel, Barefoot, and all these vendors together then came up with the INT version 1.0 specification, the data plane specification, and the report specification in 2018. And 2018 also saw general availability of solutions based on INT, such as Barefoot Deep Insight. Over the next couple of years, there were some more capabilities added, such as domain-specific instructions, more INT modes that JK will talk about, and more transport mechanisms, putting the INT headers in GRE transport and so on. So the current version of INT and the report specification, version 2.1 for the data plane and 2.0 for the report specification, were released in 2020. So some of the principles that we have followed during the development of INT, the key goal has been to leverage the programmability of P4-based data planes. Given that P4 opens up a wide range of programmability at the data plane, we want the network to be just like any like a software entity. So we want to release features and capabilities in INT at software development velocity. And of course, we don't want the applications to change. So the endpoints and applications are completely agnostic of INT underneath or any new features that get done in INT. INT is solely for the purpose of managing the network, and the applications don't have to change. And of course, given the programmability and for rapid innovation and to minimize the barriers to adoption, flexibility has been one of the key goals. So let me explain. So flexibility, by flexibility, we mean flexibility in where you can embed this INT header. If you're operating directly on the underlay, you could carry the INT header over TCP and UDP between the TCP header and the actual payload. If you're in an overlay environment, you could carry the INT headers in VXLAN or Geneve, or you could carry the INT headers in IPv4 GRE headers. The spec also allows for flexibility in modes of operation, as JK will talk more about that. And also in terms of instruction definition. So there are a fixed set of instructions in the baseline specification, but if a particular switch vendor or a particular network vendor wants to support more sophisticated instructions, that is definitely possible. And we call these domain-specific instructions. As long as all switches understand the semantics of the instructions and understand the particular domain ID, they can insert more sophisticated metadata for more sophisticated instructions. And of course, to report different metrics, and with the flexibility in metrics, you need the flexibility in report formats. And we also provide flexibility in metadata semantics. So for example, the units for queue occupancy could be cells or a fraction of queue, and so every switch vendor or every switch could follow different semantics for reporting metadata. And the monitoring engine is able to collect what metadata semantics are being used by a particular switch using a Yang model. So overall, INT has had a great impact. So we started by saying lack of network visibility was a pain point for troubleshooting, but now that there is fine-grained visibility with INT, it's a game changer, not only for simplified troubleshooting, but it opens up a lot of more use cases. For example, if you are doing the standard equal cost multipath in a data center, now that you have visibility in real time, you could choose your path for a flow more optimally, and you could do it either at a flow level or a flowlet level and optimize how your traffic is routed in the data center. You could do better congestion control, and JK will talk about some of the the use cases and some of the research and some of the industry efforts in terms of using INT for congestion control. And overall, it enables much more sophisticated network management and capacity planning. So with that, I'll hand over to JK to talk more about the INT as a system and the different aspects and modes.
Thank you, Mukesh. So I'll be covering some systems aspects and then the future direction of INT, starting from these three logical functions. So to monitor network traffic, we better identify which traffic we want to monitor from the beginning, because in some cases, monitoring every packet in the network could be a little bit overkill and then incur lots of overhead. So there is a configuration aspect, which traffic we want to monitor for which type of event. Once those traffic or set of flows are identified, the next step would be triggering function. So because if we just mirror every packet of such a 5 tuples identity, and it will still incur too much overhead for the monitoring system. So we definitely want to narrow it down to the particular events and changes that are happening in the network system, so that we will be notified only when there is information that really matters to our attention. It could be flow level events or packet level or queue level congestion events. Finally, we have such events detected from the data plane, then it's up to the system to generate a report to the monitoring system or for other entity for the closed loop control. So from systems point of view, there are such a three logical functions that we can place in different network locations, either host networking stack, NIC, or even switches. And as a result, we are going to demonstrate different modes of INT that demonstrates the different mappings between these functions and then actual network locations. And why we are doing so is basically to better meet the different set of use case requirements and also deployment constraints. For example, some customers, we found that they are fine with actually adding some additional instruction or data into the live data packet, but some are not. So different modes of instructions and also operations can support these different requirements. The first mode is we call INT MD, embed data, which is basically the classical INT where the hub devices are following the instructions added by the source switch and then stacking up the metadata into the live data packet header. So this is the best way, for example, to track the path information and all detailed information from all the hub devices in the routing path. But actually it incurs some overhead in the live data packet also to the monitoring system to go through the stack of metadata. So as a result, we took another extreme, something called INT XD, export data, also known as postcards. Here, the watch list or the configuration classifier table needs to be programmed over the hub devices in a consistent manner. And also event detection engine has to be there in all three or network devices. And then based on that, the same level of telemetry can be reported by each individual hub devices. And it's up to the monitoring system to collate such a report informations generated by the one same data packet. And like Mukesh mentioned, we have some working production level system that demonstrates collating this postcard information can give us the same level of telemetry as the INT MD mode could provide. Now, as a third step, we took some hybrid between these two modes. Here, the INT source device. In this example, we expanded the domain of INT, not just from the switches up to the host networking stack. So here, the sending host serving the role as INT source node, which insert the instructions, and all the following hub devices just perform that instructions and generate the reports. So in that case, we don't really need to configure the watch list or classifier across all the hub devices. And as an evolution to that, and also to better support something like a congestion control use case, what the INT MX mode or the MD mode can also do is showing a small amount of source data at the INT source node, and that portion of data can be read and updated by the individual hub devices. So what gives us here is that, for example, when congestion control algorithm wants to use that INT information in band, we still have such a kind of aggregate metric like a maximum congestion information, worst case congestion information aggregated in the source data, consumed by either the receiver node or echoed back to the sender node so that it can actually use as a congestion metric. At the same time, because like Mukesh mentioned, there are different standard versus domain-specific instructions instrumented in the INT spec that allows that switch monitoring the switch telemetry and then sending to the monitoring system is also possible while we are consuming the source data for congestion control use case. And another type of telemetry supported by the telemetry report spec in p4.org apps working group is drop and queue report. Drop monitoring is very important because without drop monitoring, for example, when INT MD or MX mode data got dropped, we are basically losing not only the packet, but also all the metadata carried by the packet. So this drop monitoring, which can be configured to monitor every packet experiencing some type of drop region or type of drop events, can be configured locally at each switch, and then it can the generated reports can be sent to the monitoring system and then collated with the other flow level reports to reconstruct every event, either monitor congestion or path changing or drop events happening in the network. Similarly, congestion is also a very important event. So some customers or users may want to know every flow or packet contributing to the particular queue congestion, regardless of 5-tuple, which 5-tuple flow is going into, and then reconstruct or replay that history of the queue. In that sense, the telemetry report spec can be used to generate such a queue reports. Now, let's take a look at a little bit of INT by the industry first. And when you just Google it, Inband network telemetry INT, I just found there's something like up to 300,000 of results, maybe not all of them directly related to INT, but many of them really are relevant to the particular technology we are talking about here. And actually, it exemplifies that the term INT has been used not only to indicate this particular P4-driven technology, but also as a generic industrial term to talk about many different data plane-driven telemetry technologies and services on top. With that, the particular INT specs that we talked about has been adopted and for production or proof of concept by different vendors. And at the same time, it has influenced a number of standard bodies, including SFlow and also IETF. For example, in-situ OAM, IOM, or in-band flow analyzer, IFA, are also making some progress, good progresses in IETF. Especially IOM is pretty close to be standardized as RFC. That means that the number of different INT variants are becoming really the centerpiece of the network building blocks and well adopted by these standard bodies. Okay, so in terms of deployment options, we mostly talked about the mechanism that monitors the switch as a kind of white box that can provide such a metadata directly, either in-band or as a separate packet. When in cases where you don't have such a flexibility in the network switches, and it is also possible to monitor drop or congestion status of the network while still treating the network itself as a kind of black box by monitoring only at the edge of the network boundaries. So there is one example called host INT, and then you can find more information in this GitHub repo. With that, let me jump on to the future directions of INT or network telemetry, data plane telemetry in general. I can provide you two keywords. One is the telemetry for control, either control done by SDN controller or part of the transport engine for multipathing or congestion control, while making a synergy between this network telemetry information with the existing transport level or TCP or any transport level state machine already existing in the transport protocol. At the same time, this kind of telemetry part of the transport could be an answer to improve the number of flows. For example, when we track the kind of per flow state or event detection in the switch, that means that we are kind of bound by the relatively small switch memory. So by tracking such a per flow or connection state in the transport engine, we are definitely leveraging the existing data structure that can track millions of flows in the maybe NIC hardware or host networking stack. And this can also enable us or the monitoring system to further reduce the number of reports, because then you can now make a more high-level decision based on, not only based on network fabric telemetry, but also by looking at the transport level information at the same time, and then easy to actually integrate or correlate with the application. So another kind of challenge we have found is that when you have such a network fabric information as a separate monitoring system, then even though you have a really good knowledge on what's going on the network, then you, as a second step, as a user, we want to actually correlate back to the what's really happening in the application. So correlating the application anomalies and then network anomaly is another big step, and that makes easier by pushing the telemetry boundary to the host networking stack or NIC, network interface cards. So that's a kind of high-level picture, and let me give you a number of quick examples. For example, starting from congestion control. I believe many of you are aware of something called HPCC, High Precision Congestion Control, presented at CCOM 19. And key idea is pretty simple. Instead of looking at kind of coarse grain congestion metrics like RTT packet drops or just 1-bit ECN information, INT provides precise per packet information, and you can just equate back from receiver to sender, and sender can go through the stack of INT information and make the best adjustment for either congestion window or different congestion related reaction policies. So this project has been taken off in also IETF, and we are getting pretty good interaction, and then the number of industrial partners and vendors and users are forming a group together to make HPCC as a kind of more industrial standard with more additional support for different level of telemetry and different vendors. So with that congestion control use case in mind, or maybe the consumption of INT for closed loop control as a part of transport, one particular challenge you can imagine is the overhead of processing the large stack of INT metadata in the receiver side transport engine, or maybe when it echoes back, the sender has to process this stack anyway. And the large stack overhead is also itself is a byte overhead added to the live data packets. So one thing you can think about by leveraging as a solution to that, we can leverage the existing programmability in the switching devices, and then simple compare and update policy can be easily implemented in the switches to provide min, max, or some summarization like aggregate metrics. It can reduce the large INT stack into the small constant size, which can just fit into the INT MX source data as we have looked at, or it could fit into the existing layer 2 to layer 4 header. And another form of telemetry is something we call back to sender. And it could be seen as a variation of INT XD or postcard, but instead of sent to the separate monitoring system, it's sent to the sender, so that it doesn't require any change on the data packet, and also gives the fastest possible signaling of such emergent congestion or failure events information back to senders, so that sender can make a very fast reaction to that event. And this concept is a kind of evolution of the previous people workshop talks that we presented before. So as an example of the in-network reduction, I present TCP INT, and there is a separate demo, so please take a look at the demo session for more details. But key idea is really simple. TCP has options header, and we found that such a max queue depth or minimum bandwidth metric can easily fit into the options header. And by having it part of TCP header structure, we can easily combine this with the existing TCP states like a congestion window and then smoothed RTT and make a more informed monitoring decision as well as debugging and also congestion control as it is. Another interesting point is that all the existing standard network interface cards, they support hardware offloading of TCP checksum and segmentation. And by conveying this INT information part of options header, TCP, it works nicely with existing NIC hardware offloading features. So it doesn't really incur any much meaningful performance hiccup in the end-to-end system and transport layer. Okay, the second form that we briefly talked about as a new form of telemetry is a back to sender. And here we have some simple example of 3 flows. Let's say the flow S1 and S2, they're coming from the same sender to same receiver, but actually going through 2 different paths. And then in that case, if there is one of the paths is experiencing a higher congestion, and it can be signaled directly back to sender without really changing the header format of the data packet. And such a signaling information can be consumed by the sender node and then make a better load balancing decision, for example. Or in case of flow 01, the yellow one, if it doesn't have any kind of additional path for multipath load balancing, then as a reaction to such a in-cast congestion, the sender can directly flow control, pause it for a moment, or maybe the same information can be used for the congestion control. So as an example of this, there's something called source flow control that some of us, Intel and other industrial partners, are pushing into IEEE. The key idea is really simple, that there's 2 senders, they happen to collide in the some incast experiencing a queue in the destination top of rack switch. And by leveraging some capability to learn about the information, the switch ingress, even before the packets are going into the congested queue, the switch can generate a fast reaction packet, signaling packet as a layer 3 packet, forward it back to the sender. And sender can just do the flow control over there per flow or per connection level if it's capable of. If not, the source side top of rack switch can easily just convert such a SFC signal back to conventional PFC IEEE standard mechanism so that we can do that flow control reaction also or within the sub RTT time. And this happens way faster than the end-to-end congestion signaling happening, especially when the congestion signal itself is delayed by ongoing congestion in the same 4-direction path. So as a summary, as Bruce actually very nicely shared in the introduction, INT has been, actually it was the very first application representative app from the P4. And also, I believe it's one of the most widely adopted application of P4. And it has become kind of industrial norm and being conceived as a basic building block for many different networks. And it inspired the industry standard body and also a good number of research work that you could have seen from the high top-end network venues. And as a next step, we envision this new form of telemetry, INT, with maybe in-network reduction and also back to sender signaling mechanisms can enable us to build something like a really map service that you can see in actual highway travel. Before you take a travel, you have all the information of the network, and then you can plan for it. And unfortunately, today's data center is not like that. We have to wait for the previous packets and cars going through the network and coming back and learn about what's going on, and then make a decision for the next packet. We hope we can do way better than that by leveraging such a new form of telemetry and push the network utilization and then the application performance to the theoretical optimum. Okay, that's the last slide, and I will hand it over back to you, Bruce.
Thank you, JK. That was a really interesting talk, and lots of things there to follow up on. We'll just try to maybe tackle some of the top ones. So I think one thing I picked up there kind of early on is that while we often think of INT as sort of the canonical example of how you can use P4, I think it seems like it's also possible that as INT becomes better understood, it could be implemented in other ways. It doesn't necessarily require P4. Is that a fair summary?
I think so. Where it's P4 is a language, and then even without a language, you can implement certain feature as a fixed function logic, of course. But as a maybe the question may have a linkage to why INT has started as a first P4 app. If I try to answer that question, I think there is a cost associated to adding another fixed function telemetry solution into, hardware ASIC, because there's no guarantee that particular feature will be used or not. So there is always some concern around adding another fixed function feature, and it made that kind of existing approaches and vendors reluctant to do some more innovative or explore more aggressive mechanism in terms of telemetry. And
yeah.
in some sense, telemetry has been conceived as a kind of good to have solution, not a really must-have solution in cases. So that's why P4 gave, or programmable data plane gave, a confidence for vendors to play this out more openly and also aggressive manner. And as a result, the adoption of telemetry for something like congestion control, we kind of expected, but we didn't really expect this level of enthusiasm from the industry-wide. So I think that P4-driven bet on particular technology and going into the to one extreme paid out where. I hope it answers the question.
Yeah, and it does feel to me like we're still sort of in the research stage here, and we're sort of maybe on the borderline between research and advanced development, but it's still like we're still figuring things out, which is always the time when you want to have the greatest amount of flexibility, which means a programmable solution is more attractive. So I guess one of the things I'm trying to get a handle on is like you did list quite a number of switch vendors who are supporting P4 and supporting INT, but it seems like it's probably still it feels a little bit niche to me still. Like, do you agree with that? Like, because I mean, P4 it's not in every switch by any stretch of the imagination, and then some subset of switches that have P4 would be using it for INT. So like, how do you see it as kind of, are we still early days? Do you see it growing to becoming more mainstream?
I definitely see the mainstream adoption of switch telemetry as a critical building block for next generation data center. But that doesn't necessarily mean that all those implementations or future existing implementation has to follow exactly same header format, I believe. And what we see today happening in IETF, HPCC++ draft, and also there is another kind of activities like IEEE, like I mentioned. I think those new standard amendments or the new standard activities became possible because something like a P4 INT kind of pioneered and the exploration. But at the end, final realization of such a technology in a production system may look slightly different. Header format, header bits may look slightly different, may not exactly P4 INT or IFA, something new that we will come up with together as a part of ITF activity. So I think we can decouple somehow particular header wire format and then the technology itself. As long as technology gets adopted and then flourished, then I would call it a success.
Yeah.
Mukesh may have something to add, I believe.
No, I think JK captured everything. Just to go back on your point about whether you need P4 or not, certainly, as JK mentioned, you could do this with fixed function also. But what programmability, whether it's through P4 or otherwise, what it provides you is the flexibility. As you saw, we've gone through so many iterations and so many different modes. And if you want to add a new metadata, you realize that it makes sense to capture some new state for better congestion control. P4 and programmability gives you the flexibility to do that without respinning a fixed function device.
Yeah. So one other thing I wanted to touch on is that there is a lot of flexibility, which is good when you're trying to figure out what you need, but it also creates a level of complexity. And I think you mentioned that every vendor could implement things slightly differently. They can have their own way of counting queue depth. They can use their own header format if they want. And ultimately that's kind of challenging, right? Because if what I'm trying to do is build an end-to-end network monitoring service and every vendor's done it slightly differently, I'm going to have some challenges. So how do you sort of thread that needle between wanting to give lots of flexibility, but also wanting to have a sort of manageable level of complexity?
But that's actually great and ongoing discussion. I think at bare minimum, industry has to converge on the metric definition first. When you say latency, whether this is the nanosecond or what format it is, and what resolution or queue depth, whether byte or different unit, I think it'll be really great and it's converge on metric definition as the bare minimum. And the particular protocol that we exported out is an inband or send back to sender or to the control plane, to the controller. I think it can somehow be different across different vendor implementation. Of course, that would be great to have some common set. And I'm aware of such an effort now becoming more available in popular in ITF and IEEE. That's why something like HPCC++ draft has been really well received by multiple participants in ITF, and then more and more members are actually joining that effort. And I think we are going into that direction, but it's challenging. And I believe each vendor still want to have some flexibility to differentiate by its own different implementation. So yeah, keeping the balance will be the key metric. But I think the starting point is having everyone in one place as much as possible and start conversation in the open space. We unfortunately didn't have such an opportunity that much, but now I see the opportunity is growing for both IEEE and IETF. I'm so pretty hopeful.
Yeah, I mean, I've had mixed experiences with trying to get things standardized at the IETF, but I think the intent there is always to give some kind of standard operating model to the people who have to run networks, while also allowing vendors some opportunity to differentiate themselves. And so it's a matter of trying to come up with the necessary degree of standardization without overly constraining the implementations. And again, I think the flexibility that INT has and that P4 provides at least gives you a framework in which trying to sort of get that balance between standardization and flexible implementation is possible. So look, I think that's probably a good place to wrap it up today. I think this is a very exciting area. It's it's obviously been in the works for quite a few years now, and you guys have been very involved in it. And I just want to say thanks very much for giving us the vision of where things might go from here. And I think this is a very promising area of development.
Thank you very much. And I'd like to also express our appreciation to all those members and contributors to the INT and telemetry reports back over the last 3-4 years from different companies and users and telco and also data center. Yeah, we couldn't have gotten here without such contributions and support. And we hope to be able to continue that momentum with some different use cases we have discussed today.
Fantastic. And yeah, I think that, a lot of people watching this video probably will, want to go and figure out how they can contribute. So what's the best place for people to go if they want to figure out how would they get involved?
So as you have noticed in the first slide, Mukesh and me are now former co-chairs of Apps Working Group. The new chairs have been recently kind of decided, and then they will be announced soon in the people workshop. And I know they are actually currently working on renewed set of charter for this working group so that we can take a more look at congestion control or surrounding technologies as a new focus. And I believe that new set of meetings will be set up. And so please tune into the Apps Working Group mailing list and then GitHub.
All right, fantastic. All right, well, I think that's probably a good place to end it. Thank you both for a fascinating presentation, and yeah, that was really great.
Thank you very much.